In a lot of things in life, it is what is on the inside that matters. What is inside that beautifully wrapped birthday present you just can't wait to open? Or what kind of fillings do you want in your burrito for lunch? That is often true in the electronics world as well. What is the semiconductor material used inside that power FET? Or what is the technology node used in the newest graphics processor? But in today's Tech Chat, we'll be reminded that what is on the outside can be equally important. Welcome to Tech Chat, sponsored by Mouser Electronics, where we chat with engineering experts about the latest technical innovations that are shaping and reshaping our world. Today on Tech Chat, we welcome Brian Turn from Vishay Intertechnology, where he is part of their Automotive MOSFET team. Welcome to Tech Chat, Brian.
Hello, Dale. Thank you for having me and allowing me the chance to introduce our latest technology innovations. Today, we are trying to share our story of our journey where we find the legacy package has its limitation, and we worked on a new solution to remove that limitation and to create better products. So as we improve the silicon performance, we have found that the legacy packaging such as D-Pack, D-Pack are having limitations and reaching a point of diminishing return. So we are working on a solution to remove that limitation to allow better performance to better complement the silicon. And we're going to explore the benefit of the new efficient Powerpak A/L package, which uses the latest interconnection technologies. And we're also going to introduce the benefit of the package and also the board level reliability improvements coming from these packaging. So with our latest technology, we find that we can reduce the resistance of the silicon to a micro-ohm level, where most products are in the milliohm range. For example, a 40-volt MOSFET today, that's in the D-Pack, will be somewhere around 300 micro-ohms. However, when we place this silicon device in a D-Pack, we find that the package will add more resistivity to the overall product, which is introducing another 1 milliohm to the products. So instead of getting a 0.3 milliohm device, the customers and designers are getting a 1.3 milliohm device. And if you break down these components, there's really two contributors to the overall resistance of the final products. One is coming from the silicon itself, and the other one is the packaging. And looking at the 40-volt MOSFETs, less than 30% of the total resistance is from the silicon, and over 70% is coming from the package. So the customers are not getting a product that is as good as it can be for the 40-volt. And we find that for low voltage technology, such as 40-volt, 60-volt, and 80-volt, that are really popular in 12-volt systems and 48-volt systems, are either encountering this problem or will face this problem sometime down the road. For 40-volt, 70% is coming from the package, D-Pack package. For 60-volt MOSFETs, over 50% is coming from the package. And for the 80-volt MOSFETs, over 40% is coming from the package. So it's really limiting the performance of the silicon. And therefore, we realize that this D-Pack is reaching a diminishing return for technology innovations. So we went on a journey to search for a better solution to reduce the package contribution and to introduce better products for the designers and engineers.
So, Brian, that increased resistance means, not just lower performance, but it's wasted energy. And obviously saving power is always important, but it's increased operating temperature from the heat generated. And that means typically lower reliability. So it's a bigger problem than just not getting quite the performance you want.
That's correct. The increased RDS(on) will increase what we call the conduction loss, which comes from MOSFET conducting. This can be calculated or analyzed by I square R. So I is the current square multiplied by the resistance. So higher resistance creates higher power loss, and the power loss will heat up the device. And at the same time, the RDS(on) of the device will also increase as temperature increases. So when you have a higher RDS(on) device and operating at a higher loss, it will have a higher temperature, a junction temperature, and also facing much higher RDS(on) at a higher temperature as well. So the power loss will increase quite quickly by temperature as well. So by reducing the package contributions and overall resistance of the final products, we can alleviate that power loss situation and allowing the device to operate more efficiently. This is the reason why we felt that the legacy package, although they can accommodate a pretty large die size, have high performance silicon inside the package, but for the low voltage products, specifically 48 volt to 100 volt today, it's introducing quite a high resistance to the final products and affecting the overall performance. Therefore, we find this to be problematic when we release new technology, better products today, and therefore we have gone through this journey to search for a better packaging options, packaging technique to improve the performance of 40 volt, 60 volt, and 80 volt, and 100 volt products.
So with that background, Brian, what is it about the D2 package that causes these high resistive losses?
So inside the D2 pack, it's using a wire bond, typically aluminum wires, to create the interconnection between the source region on the MOSFET device to the lead post for the source of the package. And the resistance of this current path is defined usually by the cross-sectional area for conduction and also the number of wires. More wires are in parallel, the bigger the cross-sectional conduction area. However, also this cross-sectional conduction area is also determined by the diameters of the wires. So at the same time, you have these two factors, number of wires and the size of the wire, to limit the package resistance. So it's not a very efficient way because the silicon itself has a safe bonding area as well. And so it limits the number of wires that can be bonded to the silicon. Number two is the aluminum wires are typically somewhere around several tens of millimeters in the diameters. So those are limiting factors to the package resistance. It's very difficult to increase the number of wires as there's a safe bonding area and also the size of the wires as well. So in order to improve the package resistance, we are looking to using a new type of techniques to improve the interconnection designs to drastically increase the cross-sectional area for conductions. That's one area we focus on to improve the performance of the package and to allow better performance of the silicon.
And is the drain connection made through the back side of the device using like a conductive paste or some similar compound?
Yes, the silicon is soldered to the drain pad. So the drain terminal is directly connected to the drain pads. That is a very efficient connections. The limitation is at the source because of the source wires, number of source wires, and the size of the source wire. That limits the cross-sectional area for conductions. And imagine this is like a car traveling on a street. The traffic on one of the streets, the other two are going to get crowded. And if a street of one lane will be have higher chance of a traffic than a street of having a 3 or 4 lanes. So that's the concept of cross-sectional area for conductions. And therefore, you have the source wires has that limitations because it's limited in its diameter size and also the number of wires we can bond safely on a silicon itself. So because of this limitation of the package construction of D2 pack, we are looking for a more advanced approach to bring out the performance of the silicon. And therefore, we're looking at introducing the bond wireless constructions to Powerpak A/L and a smaller version of that package, which is the SOA-L package. As the name suggests, the bond wireless construction, inside the package, we remove all the wires for the gates and the source, and we replace interconnection with metal clips. So there is a gate clip for the gate connection, and there's a source clip for the source connections. The benefit of using a source clip is that it drastically increases the cross-sectional area for conductions, which reduces the resistivity of that interconnections. imagine this is maybe 10 times more wires being placed on the silicon itself. So we can reduce that package contributor resistance through this particular constructions. While at the same time, this construction technique, because it removes all the wires, it also reduces the parasitic inductance inside the package. And then there's another benefit from this packaging process is that the solder, the source clip and the gate clips are soldered onto the die. So comparing to a wire bonding process, this manufacturing process introduced less stress to the silicon. So we can actually use a thinner silicon instead of using a thicker silicon thickness, and we can grind the silicon down to a 50 micron to further improve the RDSon. And with a thinner die, we're reducing the elements of the thermal resistance from the thickness of the silicon itself. So now we have a construction that feature devices with lower on resistance and also lower thermal resistance to improve the thermal transfer performance. And then outside the package for the source and the gate leads and the source leads have going shapes. And the benefit of having a going lead is that it has the flexibility to provide a stress relief for mechanical and the thermal stress.
And so now you're thinning your device because this is a vertical conduction device, right? So your current is flowing vertically through the device as opposed to a more traditional MOSFET in a logic process that would be horizontal.
That's correct. Our MOSFETs are the trench MOSFET with a vertical structures where the drain is at the bottom of the silicon and the gate and source is located on the top of the silicon.
And you mentioned the force in the bond process, using an ultrasonic bonder or a wedge bonder. That's one thing that, a lot of times people don't think much of. But yeah, as you're trying to thin that silicon down, that force becomes really significant relative to the stress you're putting on that thinned die.
Right. So during the bonding process, there will be a pinch. And so for wire bonded products, we use a thicker silicon and we also have a thicker top metal to withstand the stress during the assembly bonding process. However, with the bond wireless construction, because the clips are soldered onto the silicon, so it's a lot less stress induced onto the device, and we can use a thinner die to improve performance.
Yeah, it's a fascinating solution.
So comparing to the conventional wire bonded solution in the D² pack and the bond wireless solutions in the Powerpak 8x8L, the D² pack, the package resistance determined by the diameter and the number of bond wires for the source interconnections. So both factors are quite limited, and it has a smaller cross-sectional area for conductions and also higher parasitic inductance. Now, with the bond wireless construction, we have removed all the wires. So the parasitic is minimized, and the package resistance is also improved by over 83% with the adoption of the source clip because of the enlarged cross-sectional area for conduction. At the same time, the maximum die size the 8x8L can accommodate is very similar to a D² pack. So the silicon itself, the electrical performance are quite similar. However, we're reducing that package contributions by reducing the package resistance by 83%, and that allows us to drastically reduce the resistance of the finished products and improve the performance.
Yeah, that's really remarkable. I mean, normally in the engineering field, if you can get 10% or even 20% improvement, that's a lot. And now you're saying 83% improvement over the D² pack for your Powerpak. That's really amazing.
Yes, effectively, we're increasing the cross-sectional area for conduction by quite a lot. Imagine wire bonding is traveling on a boulevard, and bond wireless construction is traveling on an 8-lane highway with no speed limit. So that's where the big differences comes from, right? Is that there's more areas for the currents to flow, and at the same time, this clip also has a heat slug to cool off the silicon as well. So the benefit is not just the electrical, it's also thermal benefits as well, and reducing the parasitic inductance at the same time.
Yeah, here is an example of a picture's worth 1,000 words here. The solution that you guys are proposing is, just substantially more elegant. So I'm excited to learn more.
So we mentioned about the 83% reduction of package resistance. This drastically affects the ratio between the package contribution and the silicon contribution. In a standard D-square pack 3-liter version, a 40-volt device where 71% of the resistance comes from the package. With the new wire-bond wireless construction in the Powerpak 8x8L, we can reduce the package contributions to 23%, where the silicon contribution is 70% of the total resistance. So now we have a product that is closer to the actual performance of the silicon. So the customers are buying a much higher performance products with the 8x8L package. This new construction is more optimized for the more advanced technologies, because now the final product is closer to the performance of the actual silicon. So the package resistance for the 8x8L is roughly around 100 microohm range for this package, where the D-square pack is over 600 microohms, and that's where the 83% improvement brings to in absolute value.
And I assume that it's your team looking at the left part of the graph where you're trying to improve performance, and the biggest problem is the package, not the silicon. So that's why you guys have invested in developing this new package technology.
Yes, putting a lot of engineering effort in improving the silicon, we're able to create products in microohm range for a wide range of breakdown voltage ratings, 40 volt, 60 volt, 80 volt, and even with the next generation of 100 volts, we are able to push the on resistance to very close to 1 milliohm and less. However, if you have a package that also add another 1 million to the final products, it's not a very good vessel for the silicon. It can double the resistance of the final products, even up to 100 volts very soon. This is the reason why we realize that it's no longer a viable solution for us to use this package. We have to find a package that's more efficient. The silicon can really leverage the package to bring better performance for customers. And that's the reason why we developed this bond wireless constructions in this Powerpak 8x8L package, and also in a Powerpak SO8L package. And also we have some smaller options available with that bond wireless construction as well to minimize package contribution.
You're talking about the package and the comparison here of the performance, but why don't you tell us a little bit, Brian, about the physical characteristics and how they compare?
Another area that the 8x8L and the bond wireless construction brings is we can shrink the package size footprint. So the Powerpak 8x8L has a typical dimension of 8.1 millimeter by 8.1 millimeters, and the height is 1.6 millimeters. And for D-square pack, it has a dimension of roughly around 10.4 millimeters by 15.9 millimeters, and it has a package height of 4.5 millimeters. So when you compare these two packages, the footprint of 8x8L is about 60% smaller. Comparing to a D-square pack's 165 millimeter square, 8x8L captures roughly around 64.8 millimeter square of PCB real estate. And also, when you compare the height of the two packages, the 8x8L has 1.6 millimeters height comparing to a 4.5 millimeter height for a D-square pack. It's 64% thinner. And another areas that this 8x8L package improves is the weight saving. Per package, the weight is about 0.3 grams, while D-square pack has a weight of 1.5 grams. So this translates to 80% weight saving per device. Not only we're introducing better electrical performance with the 8x8L bond wireless package, we're also offering a smaller and a lighter and a thinner parts to help customer increase power density for their design.
And now some people listening to this might think, well, what do I care about the weight of a package like this in an automobile? But that really relates to the reliability and things like vibration and shock environments, correct?
That's correct, yes. It adds less stress to the PCB. So just to quantify the electrical performance of the two devices, we take a 40-volt device in the best 40-volt device in an A/L package, and we also take our best 40-volt device in a D2 package. And we want to start with the RDS(on), and this is showing. This is an actual measurements of RDS(on) by currents. So we increase the drain currents of the device, and we measure the on resistance of the each device. For A/L device, from 40 amps with a low currents of 40 amps to 90 amps, the RDS(on) doesn't change very much. It stays somewhere around 0.4 milliohm. And for the D2 pack, at the low current, the RDS(on) is a little bit less than 1.2 milliohm, but as the current increases, the junction temperature also increases, and which leads to the RDS(on) increase to 1.6 million range. So this is a clear showing that the new package that has the advanced constructions where the RDS(on) is more stable across a high current range from 40 amps to 90 amps, while the D2 pack, because it's not as thermally efficient, the RDS(on) can increase with the higher current. So overall, with the similar size silicon inside the two package, because the A/L has lower package contributed resistance, we're able to reduce the overall resistance of the final products by 69%. Here is a very good example of both products. The silicon inside is roughly around 24 millimeters square, but the A/L package can achieve more or less 400 micron, while the D2 pack is at low currents, it's a little bit under 1.2 million, but as current increases, it can go up to 1.6 million due to the increased temperature. So we take these two parts and performed another test. It's a constant power test to understand the power loss of the two devices and how the power loss of the device across the low current range. So because the A/L package has lower RDS(on), it naturally has a lower power dissipation, power loss from 40 amps to 90 amps. At the 90 amps level, where the parts are still remain to be somewhere around a little bit less than 0.5 million, the power loss is below 4 watts. For D2 pack, because of the increase, the RDS(on), the power dissipation is roughly around 13 watts due to higher RDS(on). So this experiment shows that the A/L generates lower power loss because of the improved RDS(on) and actually adds less thermal stress to the overall systems.
So what about the thermal performance of these packages, Brian? How do they compare?
We also measure the temperature from this testing across the current range. Because A/L generates much less power loss, 4 watt versus 13 watts. Naturally, the device actually has lower junction temperatures, especially at 90 amps, a very high current level. A/L is measured at 80 degrees C, where the D2 pack reached very close to 120 degrees C. So there's almost a 40 degrees C difference when you compare the two package at 90 amps. This shows that the SQ-JQ140ER, the A/L package, has, because of its lower RDS(on), it generates less power loss. Therefore, the temperature rise is lower, allows the operations to run cooler, and at the same time, the customers can have a system that has less thermal stress, and perhaps even affecting the simplification of a thermal management system, because the package allows the silicon to run more efficiently.
Yeah, that's a really important point, Brian, because it's a multiplier effect of the cost of the total system because you're having to try to run hotter or to add more cooling to keep it from overheating. Now, we've kind of talked generically about the packages and some of the performance here. Why don't you show us what it means for the spec improvements for people that are going out and purchasing some of your NFETs and your PFETs?
This new package allows us to enable products in micro ohm levels. In terms of the actual performance of the finished goods, for 30 volts, we can generate products less than 500 micro ohms. 40 volt, we have products that's less than 530 micro ohms. And for 60 volt today, we offer products that's less than 800 micro ohms. And for the 80 volts today, we introduced a 1.4 million device. And our best 100 volt products in an A/L package, it has 2.5 million. With the next generation silicon, we're expecting another 25% improvement across the board for 40 volts to 100 volts. And this is pretty critical for 12 volt system and 48 volt systems, particularly for power steerings, battery management systems, and e-fuse, relays and load switchings and liquid pumps. These applications tend to have higher currents, so they need components with very low resistance to reduce the conduction loss. And also at the same time, because the reduction of conduction loss, they can perhaps optimize the thermal management. They can have further optimization to increase power density. So this package really allows us to move forward with the technology evolution. While we introduce better silicon, really new silicons better to allow performance of the latest technology by minimizing the conduction loss. The benefit doesn't really stop at the N channel. It also positively impact the P channel devices as well. For our 30 volt P channel, we have a 1.2 million device in the A/L package. And also for 40 volt P channel, we have a 2 million device as well. So those typically, the P channel parts are either in a reverse polarity protections or in low switching or power switch applications. And all of these applications also requires a very low audio sound. So with the new bond wireless constructions, we are able to really upgrade the performance of our entire portfolio and giving customers some of the best industry-leading products in the market today.
Yeah, Vishay was already one of the leading power FET companies in the industry, so applying this new packaging technology to your existing line is pretty exciting. Now, Brian, for engineers that already have existing designs using some of the older, more standard power transistor packages, can you provide some recommendations for transitioning to the new Powerpak packages?
We have worked with various customers to form a plan to the migration from the legacy packages to the Powerpak package family. For the D2Pak 7 lead package types, we recommend customers to investigate or to experiment with our Powerpak A/L and A/LR. So we have two versions of the Powerpak A/L package. One is the standard L package. The drain pads is at the bottom of the package that utilize the drain for the primary thermal transfer path. However, we also have a second version we call A/LR, a reverse version of the package, where the drain pad is moved to the top. And this allows customers to use these packages with the heatsink. So the best way to use the LR is connecting the MOSFETs, this A/LR package to a heatsink. So the heat, instead of going down to the PCB, escapes from the top of the package into the heatsink. With the A/L and LR package, these two package types are 50 to 60% smaller than the D2Pak and D2Pak 7 leads to reduce the PCB real estate footprints for these packages. And for the D2Pak, we recommend experimenting with Powerpak SOA-L bond wireless package. So this new SOA-L package has a footprint size of 31.3 millimeter square comparing to a D-Pak. It's roughly around 64% smaller. And another popular solution is the SOA-L package. We have two different versions that can provide an alternative to the SOA. It's the Powerpak 1212-8 SLW, which has higher performance, And then the slightly higher RDSM version of with the same footprint size is the Powerpak 1212-8W package. The W represent the wettable flank features for these package. The wettable flanks actually promotes the better solder fillet formations, so the customers can perform AOI on the solder joint integrity, which improves the reliability and reduced field return in the future for the final product.
So this has been really interesting, Brian. What else do you have for us today?
So beyond the performance improvements, we also have several board level reliability is another areas we focus a lot on. Is making sure the products has high board level reliability. Not only just providing a better electrical performance, but also reliable and reduced field returns. So one of the key area that we focus on is the board level reliability of the package. This is related to the solder fatigue, either electrical or mechanical stress. Because mission critical applications, reliability is a very it's probably the most important factors in terms of designs. So when we design our package, develop new packages, board level reliability is very high on our list as a design goal. So inside this package, we use this dual clip construction that we went through extensive analyses and simulations to make sure that it reduces the stress on the die and the leads while providing very low resistance and inductance. And also because we can shrink the package by 60% compared to a D-square pack. Smaller package tend to have less thermal mass as well. So with a smaller package and less thermal stress, it's introducing a less thermal stress to the overall PCB assembly. And the shape of the going leads are also designed to achieve maximum mechanical and thermal stress relief due to the inevitable expansion and contractions during a thermal cycling environments. And the mold compounds are also very carefully selected and tested because these mold compounds features customized properties to reduce the CTE mismatch and also reduce the stress for board level reliability.
This is a good reminder, Brian, that while the transistor technology or the IC technology gets a lot more of the press, the engineering that goes into just building the packages is pretty incredible.
There's a very high level complexity in the mechanical, trying to reduce the mechanical stress and the thermal stress of the products. We recognize that the Powerpak A/L and SOAL tend to be used in medium to high power application, meaning that from several hundred watts to thousands of watts in the applications. So the systems with these type of MOSFETs inside the system tend to have thermal and mechanical stress as well. And therefore, we wanted to reduce the risk of solder fatigue due to the stressful environments from the stress. Therefore, we examine a couple areas, not just the overall electrical performance, but we look at how the interconnections are designed and integrate with the overall package constructions. And also the going lead shapes has gone through analysis to have the design has the right bending angles and also have the right height to allow maximum mechanical and thermal stress relief. And another element is that there's a CTE mismatch between materials. And the higher the CTE mismatch, there's a higher chance of failures in thermal stress environments. So we work with our mold compound vendors carefully to have proprietary type designs for the mold compounds. And all of this contributes to a higher board level reliability. So we have taken the design approach to improve the board level. Not only we take the design approach where we thought we can improve the board level reliability, we also put these new packages to board level reliability testings, actual testings to prove that the design concept actually meet our original goals to improve board level reliabilities. And the tests we have performed on the A/L include bending test, vibration test, rapid thermal cycling, and power temperature cycling. So these are all tests that's very rigorous stress to the package. We monitor the test results and also confirm that there's no solder fatigue after the test to make sure that the integrity to PCB is good to achieve high board level reliability.
Yeah, that just fits what we've kind of been talking about. These smaller, lighter packages are kind of intuitively will perform better. It's a smaller package to bend. There's less mass moving during vibration. There's less area and thermal mass when you're power cycling. So it really makes perfect sense that this better package is going to perform better.
So not only we have a standard version of the package where the drain is at the bottom of the package, we understand that a lot of customers like to use TO packages, transistor outline packages with heatsink. A lot of times they will bend up the leads to have the drain pads facing towards the enclosure or facing towards the heatsink, using the heatsink or the enclosure to dissipate heat from the MOSFET. So with that application in mind, we also released a version of A/L with a topside cooled feature, where the drain pads is on the top. So this package has the pin configuration is very similar to a standard package, where there's 4 drain pins, 3 source pin, and a gate pin. The difference is that the drain pads is now at the top of the package to allow contact to the heatsink or the enclosure. So the way to use this package is that you can place a thermal interface on top of the drain, and then this drain pads can connect it to the heatsink directly. And also the package has the going leads to allow stress relief, improve the board level reliability. Inside the package, it also has the wire-free construction, which we have removed all the wires, bond wireless constructions. The gate and the source interconnections are utilizing a metal clips to achieve low electrical resistivity and also very low parasitic inductance. For a 40-volt device, the RDS is as low as 540 microohm. It can use the same silicon that we encapsulated in an A/L standard package. So the electrical performance is very similar to the standard counterparts.
So what does this look like when you use the reverse Powerpak design and attach it to a PCB?
We can start by looking at the standard package first. For standard A/L, it's usually connected to a PCB. So for A/L standard surface mount package, usually it's connected to the PCB, and the PCB has thermal vias and also copper contents inside to extract the heat from MOSFETs. And to cool off the PCB further, the PCB will be attached to a heatsink or a housing. So there's a few elements in here where the heat travels from the package to the PCB and to the heatsink. The thermal transfer for the MOSFET is not so direct. It has to go through a couple elements that introduce thermal resistance. The PCB and the interface between the PCB to the housing or the heatsink and the heatsink itself. Now with the topside cooled versions, remove these elements, the PCB, where the package can be connected to the heatsink or the housing directly with the thermal gap fillers in between. So right now, with the A/LR, the thermal path will be going from the device to the thermal gap filler to the heatsink. So the extra layer of PCB has been removed. Now this brings several benefits to the overall design. One is that because the primary thermal transfer path is from the top of the package to the heatsink, we can reduce the thermal vias on the PCB itself, which allows the PCB size to shrink slightly. Because the thermal management relies on the heatsink, PCB is no longer the dominant thermal path. So the remaining components can be rescaled and scaled down as well. Now, with the scaled down components and the removal of thermal vias, the PCB can be smaller and more simplified, and at the same time, having increased the power density of the overall design. So this really allows a more effective usage of the heatsink and the enclosure to transfer heat.
Well, that's really interesting, Brian. We're kind of approaching the end of today's Tech Chat. Can you provide us a review of some of the key things we've learned in our discussion today?
So the new Powerpak packages, because of their bond wireless construction, reduces the package contributions. It allows minimization of RDS(on) and also allows the reduction of power loss with the lower RDS(on). Now, combining the performance of improved electrical specifications and also smaller and lighter physical attributes, the new packages help increase power density from using transistor outline packages. We also offer a topside cooling package options to enable low RDS(on) devices that is optimized for heat sinking. And when we develop these packages, we put these new package concepts through extensive stress testing to ensure the board level reliabilities. So with these new package concepts, we offer increased performance and reduced potential field failures.
Thanks, Brian, for introducing us to the hottest new packaging technology from Vishay, hot tech to keep our systems running cool. Now, for our audience that is looking to learn more, where should they go?
Thank you very much for giving me the time to introduce our new technologies. And if there's more questions about our products, please feel free to visit Vishay.com and our Vishay Automotive MOSFET webpage for more information.
Thanks, Brian. And if anyone is interested in any of the technology we've discussed today, I'd encourage you to head over to Mouser Electronics, our sponsor for today's Tech Chat. And please join us again next time on Tech Chat, where we chat with the leading technical experts like Brian Turn from industry-leading companies like Vishay, who are changing our world every day.